Welcome back to the Crash Course Trigonometry series. In this video, I'm going to talk about some additional trigonometric identities. So specifically, I'm going to talk about the sum and difference formulas for sine and cosine, and I'm also going to talk about double angle and half angle formulas. So the first thing I'm going to talk about is the cosine of the difference between two angles. So in this case, I'm calling my two angles alpha and beta. So I'm looking for a way to understand the value of the cosine of alpha minus beta. And the proof is actually not too difficult to understand, so I haven't gone through too many proofs of formulas in this series, but I think this one's pretty neat and worth taking a look at. So what we've got here is two different ways to think about alpha minus beta. So in the diagram on the left, I've got the two separate angles, alpha and beta, and just for the sake of argument, we're saying that alpha is a larger angle, although this argument works either way. And then the distance between the point on the unit circle corresponding to alpha and the point on the unit circle corresponding to beta is this segment here that I've written with the orange segment. But the other way that I'm going to look at that distance is by subtracting alpha minus beta and thinking of that angle in standard position. So the distance here is the same, but now I have two different ways to think about the same distance. So what we have is that the distance from cosine alpha comma sine alpha to cosine beta comma sine beta is equal to the distance from cosine alpha minus beta comma sine of alpha minus beta to the point 1 comma 0. And we're just going to use our distance formula. So the distance formula says that the distance is the square root of the difference in the x-coordinates squared, so that's cosine alpha minus cosine beta squared, plus the difference in the y-coordinates squared, so that's sine alpha minus sine beta squared. And that's going to equal the same type of expression on the other side. So that's going to be the difference in the x-coordinates so cosine alpha minus beta minus 1 quantity squared, plus the difference in the y-coordinates, so that's sine of alpha minus beta minus 0 squared. Now I'm going to FOIL out all of the, well, first of all, I'm going to square both sides to get rid of the square roots. So I'll use my trickery on my tablet here to just get rid of the square roots. So I've just squared both sides. And now what I'm going to do is multiply out those squares. So on the left-hand side, when I FOIL out cosine alpha minus cosine beta, I'm going to get cosine squared alpha minus 2 cosine alpha cosine beta plus cosine squared beta. And then I'm going to square out sine alpha minus sine beta. And similarly, using FOIL, I'm going to get sine squared alpha minus 2 sine alpha sine beta. And that's going to be plus sine squared beta. And the right-hand side is going to do the same thing. So cosine alpha minus beta minus 1 squared, when I multiply that out, I'm going to get cosine squared of alpha minus beta minus 2 cosine alpha minus beta plus 1. And then I'm going to get, when sine alpha minus beta minus 0 squared, I don't have to FOIL that out because when I subtract 0, nothing happens. So I just get sine squared of alpha minus beta. And now I'm going to use my trigonometric identity, my Pythagorean identity, several times. So on the left-hand side here, I've got cosine squared alpha plus sine squared alpha. That equals 1. And then I've also got on the left-hand side cosine squared beta plus sine squared beta. That also equals 1. And then I've got minus 2 cosine alpha cosine beta. And then also minus 2 sine alpha sine beta. And on the right-hand side, I've got cosine squared alpha minus beta plus sine squared alpha minus beta. That's 1, again, by my Pythagorean identity. And then I've got minus 2 cosine alpha minus beta plus 1. And now I'm going to subtract 1 from both sides twice. So I'm going to subtract 1 from both sides, that gets rid of those. I'm going to subtract 1 from both sides again, that gets rid of those. And then everything has a negative 2, so I'm going to divide both sides by negative 2. So that's going to give me the cosine of alpha minus beta is equal to the cosine of alpha times the cosine of beta plus the sine of alpha times the sine of beta. And that's my formula for the cosine of the difference between two angles. So it's really just using the distance formula and some algebra. So if we want the cosine of the sum of two angles, all we have to do is think of cosine of alpha plus beta as cosine of alpha minus beta. And so when we use our formula for that, so alpha plus beta is cosine of alpha minus beta. Our formula for the cosine of the difference of two angles is the cosine of the first angle times the cosine of the second angle plus the sine of the first angle times the sine of the second angle. Now cosine, as we've seen, is an even function. So cosine of negative beta is just the same as cosine of beta. But sine is an odd function, so the sine of negative beta is actually negative the sine of beta. So this is sine of alpha times minus sine of beta. And so that's going to be cosine alpha cosine beta minus the sine of alpha times the sine of beta. So a very similar formula to what we had before, but with a minus sign. So that's our formula for the cosine of the sum of two angles. So we can do the similar kind of process, similar kind of arguments for the sine of the sum of two angles. So here is a summary of all of the four formulas that we have for the cosine of the sum of two angles, the cosine of the difference of two angles, sine of the sum of two angles, and sine of the difference of two angles. So they're good, those are good things to know. Now, there's a special case of these sum formulas, which is when the two angles are the same. And this is really a pretty useful thing to know for a few reasons that I'll talk about a little later in this video. But what happens is we get what we call double angle formulas. So the the cosine of 2 alpha, we can think of that as the cosine of alpha plus alpha. And then it's the formula that we have before. We're just having the two angles are alpha and alpha rather than being alpha and beta. So this here is kind of like the beta, the second angle. It just happens to be the same as alpha. So we get cosine alpha times cosine alpha, that's cosine squared alpha. And then we get sine alpha times sine alpha, that's sine squared of alpha. So we've got cosine squared alpha minus sine squared of alpha. That's our formula for the cosine of 2 alpha. So if we have the sine of 2 alpha, same kind of thing, we're going to think of that as sine of alpha plus alpha. On the previous slide, I showed you the formula for the sine of the sum of two angles. And that gives us sine of alpha cosine of alpha plus cosine of alpha sine alpha. Well, those are the same. I'm adding the same thing to itself twice. So I get 2 times sine alpha cosine alpha. Now, there are other forms for the cosine of the double angle, which are going to be useful a little bit later. So one of the things that we can do is use our Pythagorean identity to replace cosine squared with 1 minus sine squared, right? We know that the cosine squared of alpha plus the sine squared of alpha is equal to 1. So that means that cosine squared of alpha is 1 minus sine squared of alpha. And it also means that sine squared of alpha is 1 minus cosine squared of alpha. So one thing I can do is replace cosine squared of alpha with 1 minus sine squared. Or alternatively, I can replace the sine squared of alpha with 1 minus cosine squared of alpha. And both of those replacements are going to give me a different looking formula for the cosine of the double angle. In this case, I'm going to get 1 minus 2 sine squared alpha. And in this case, I'm going to get 2 cosine squared alpha minus 1. So those are also formulas for the cosine of the double angle. So here's a summary of the double angle formulas that we got for sine and cosine. I've just replaced the alpha with a theta here. That's typically the way that you would see this, or you might see it using an x or a different variable. You want to leave it as alpha, that's okay too. Something else that we can do with the cosine of the double angle is we can actually take those alternate formulas that we found and solve them for the sine squared or the cosine squared. So recall that we had cosine of 2 theta is 1 minus 2 sine squared theta. We also had cosine of 2 theta was equal to 2 cosine squared theta minus 1. So on the left-hand side, if I want to solve that for sine squared, what I can do is add 2 sine squared theta to both sides, subtract cosine 2 theta from both sides, and then multiply both sides by 1/2. So that gets me sine squared of theta is 1/2 times 1 minus cosine of 2 theta. And on the right formula here, I can just add 1 to both sides. So 1 plus cosine of 2 theta is 2 cosine squared theta. And then multiply both sides by 1/2. I get cosine squared of theta is 1/2 times 1 plus cosine of 2 theta. And because 2 theta, well, because theta is half of 2 theta, we sometimes call these half angle formulas. Now we could take the square root of both sides at this point, but that would give us a plus or minus. And what you'll see if you continue on and take calculus, you'll see that these half angle formulas are actually pretty useful for certain applications in calculus. So I'll leave them here, but we could theoretically use these with a square root, although we'd have to use analysis like we've done before using quadrants and figuring out whether our sine and cosine are positive or negative to deal with the plus or minus that we would get if we took the square root of both sides. Okay, so here's a complete summary of all of the identities, all of the formulas that we found in this video. No, it's a lot of formulas, a lot of things to remember, but these are all useful things that may be handy when you study these functions. So next time we're going to talk about the law of sines and the law of cosines, and that's actually the last video in this series. So I will see you then.